A little while back, we covered the cleanest EQ possible, using an FFT editor like Isotope RX to reduce or increase the amplitude of frequencies. Although it results in less distortion than any EQ plugin, it's a bit cumbersome to use. Fortunately, this is not the case with compression. One developer has created what's possibly the cleanest compressor plugin currently available. So whether you need to compress vocals, instrumentals, or full stereo mixes, let's cover the cleanest compression possible. Starting off, we need to cover audio compression and the Hilbert transform. So I'm going to keep this section pretty brief since this is a topic for a mathematics professor, which I'm definitely not. But in short, the Hilbert transform consists of measuring EEG signals and assigning the signals as real data. Then, by rotating positive information by 90 degrees, we're provided with the needed imaginary data, and at this point, we have enough information to convert that data into measurements of the frequency, the amplitude, and the phase angle. Now that's a simplification of how it works for sure, but the key takeaway here is that it allows for very accurate measurements of everything that's needed to reproduce an audio waveform. Like FFT processing, the Hilbert transform can recreate more accurate divisions of a signal's amplitude, frequency, and phase. So next up, we need to understand how amplitude accuracy relates to total harmonic distortion. If a processor mismeasures a waveform, it'll distort it. For example, if a waveform looks like this, so a symmetrical sine wave, but a processor either inaccurately measures or purposefully processes the wave with the peak and the trough clipped, the differential between the original wave and this reshaped wave is harmonic distortion. Now that's because the differential is a new waveform with a length that corresponds to the length of the original waveform. In other words, this shorter oscillation is a multiple of the original oscillation. So, if the original sine wave was 100 Hz and this new waveform is 300 Hz, the synthesized or new waveform is a third-order harmonic. Now this means that if a processor could measure a waveform perfectly, no distortion would occur, again unless it purposely shaped the waveform or it introduced a different process that causes distortion. Now to demonstrate this, here's this free ADC drive plugin. The green points represent the peaks and the troughs of a sine wave that I'm feeding into the plugin. As I increase the input and shape the wave, the differential between the input and the output creates harmonics. As the peaks and the troughs are reshaped, multiples of the original signal, in this case 100 Hz, are generated and become higher in amplitude, the greater the differential between the input and the output. So we'll notice 300 Hz, 500 Hz, and so on. All this shows that if we want incredibly accurate processing with little to no harmonic distortion, then we need a processor that's capable of accurate measurement so that the input waveform more closely matches the output waveform and vice versa. So this brings us to the question, what is the cleanest compressor? So when I was testing compressor plugins last week, I came across something strange. This Tone Boosters compressor behaved like most compressors that I've encountered. It affected dynamics, and it left the frequency response alone except for the harmonics it introduced. However, I noticed that as I switched from algorithm to algorithm, one stood out. Whereas most compressors, with a moderate attack and release, increased the THD by about 30 dB on the lower end and up to 120 on the higher end, this compressor's punch algorithm increased it by only 3 dB. So thinking I had messed something up, I tested a bunch of compressors. When that didn't give me more insight, I read the manual, and finally I just reached out to the developer who had this to say. We don't want to reveal all of the secret sauce to create high-quality plugins, but yes, Hilbert transforms are an essential ingredient to create low latency, low THD compressors as they alleviate any estimation errors when measuring levels of tonal signals, which is an essential part for low THD. Now when I pressed for a little bit more info on this Hilbert transform, he responded with, Hilbert transformers are quite complicated and the relation between a Hilbert transformer and a compressor sidechain is probably only suitable for an explanation in an academic paper. Winky, smiley face. Now this made me feel a bit better about not fully understanding some of these finer details, but the practical takeaway is that it looks like the Hilbert transform's accuracy in this compressor and with this particular punch algorithm creates some of the cleanest compression possible. This is particularly true when it's combined with an attack above 10 milliseconds and a release above 50 milliseconds to ensure that the compressor's attenuation isn't quicker than the waveform's full oscillation. Now, I'll compare this setting to other compressors in just a moment, but for now, let's take a listen to our signal attenuated with these settings and let me know if you can hear any distortion. Real quick, if you want to get your mixes to sound like professional songs, we have a mixing membership called the Sage Audio Membership, where you get access to Sage Audio University for in-depth mixing and mastering courses, private one-on-one mentorship, and personalized mixing feedback. Go to sageaudio.com or use the link in the description. Next up, let's cover other compressors and why they distort. Now, one big reason compressors distort is the attack and release times. No compressor can really avoid this. For example, if I use the Tone Boosters plugin, but with a lower attack and release, or both, we'll achieve harmonic distortion. Now, the compressor is moving faster than one full oscillation. When it attenuates before the oscillation completes, wave shaping occurs. This differential between the input and the output results in harmonics. Since lower frequencies have longer wavelengths and require more time for a full oscillation, these distort more often. So, if the frequency is 80 Hz or 80 oscillations per second, we could divide 1 second by 80 to find the time of one oscillation in seconds. This results in 0.0125 seconds or 12.5 milliseconds. So, attack and release times shorter than 12.5 milliseconds will typically distort an 80 Hz wave. Now, other variables play a role, but look at how harmonics form right when the attack time is reduced to below 12.5 milliseconds. Next, as we covered earlier, the other main causes are inaccurate amplitude measurement and any purposeful wave shaping introduced by the plugin. For example, if we take a look at the Pro C2 plugin and select its punch algorithm, with a 12 millisecond attack and a 50 millisecond release compressing 80 Hz, the THD is negative 37 dB. Now, this is most likely on purpose from the developers. That said, if we switch to the mastering algorithm, notice how the THD drops to about the same level as Tone Boosters when it's set to its punch mode. Interestingly though, the Pro C2's mastering algorithm introduces significant distortion at extreme low and high frequencies if oversampling is off. In contrast, Tone Booster's compressor introduces significantly less distortion at extreme lows and no distortion at extreme highs. Now, even though the amplitude in a track might be too low at the extreme lows and the extreme highs to trigger the compressor when processing only that frequency, remember that could still be compressed when another range triggers the compressor, since the full spectrum will be subject to compression. So, let's take a quick listen to these two compressors on the same segment of a mix. Let's look at one more compressor that's said to sound clean, the Weiss DS1 Mark III. Although I really enjoy this compressor, calling it clean isn't too accurate. It sounds great, but the distortion it introduces is pretty significant. Not something that you'd want to use for most mastering applications, although that's totally up to you or the engineer that's mastering. That said, if the goal is to alter a signal's timbre as little as possible, this probably wouldn't be a good choice. Let's compare the two compressors while using identical settings. In this case, you should hear a little bit more of a difference than in the previous example. Last up, let's cover some possible complications with Hilbert transforms. So one concern I've seen about using Hilbert transforms in audio plugins is the somewhat unknown consequence of phase rotation. Remember, 90 degrees of rotation is needed for the processor to measure the amplitude, the frequency, and the phase angle correctly. Although this is an understandable concern, phase rotation should be inaudible if it occurs to both the left and the right channels identically. Now, that's why I could invert the polarity of a master, and you wouldn't be able to tell the difference. The amplitude is the same, the frequency is the same, while the phase angles are equal and opposite to what they were. Now granted, inverting the polarity is a 180-degree rotation, whereas the Hilbert transform requires a 90-degree rotation. That said, mastering engineers have been rotating the phase of a mix for a while now to ensure that the peaks and the troughs are accurately represented, in other words, to ensure that the mix doesn't have an offset before it hits a processor. So it seems that our inability to cue in on identically shifted phase angles kinda comes in handy here. As for excessive latency, it's easy to understand why some would be skeptical about a low-latency FFT-adjacent form of processing. After all, FFT processing in an audio editor could be so CPU-intensive that it requires a separate platform. However, it looks like computers can quickly introduce the Hilbert transform. The Tone Booster's compressor requires 144 samples in a 48 kHz session, so it takes only 3 milliseconds to make the needed changes to the input. Overall, it's exciting to see this form of measurement have such a beneficial effect on a processor's accuracy. Now, we've talked a lot about this plugin, so let's spend some time listening to it. I'm going to use subtle settings on a full mix and vary some parameters. The effect should be transparent attenuation of peaks, meaning no alteration to the mix's timbre, just controlled dynamics. As I mentioned earlier, if you want to get your mixes to sound like professional songs, we have a mixing membership called the Sage Audio Membership, where you get access to Sage Audio University for in-depth mixing and mastering courses, private one-on-one mentorship, and personalized mixing feedback. Go to sageaudio.com or use the link in the description.